Have you ever just stopped and noticed how the world around us is absolutely filled with the most incredible patterns? From the way a flower blooms to even how we save money, there's this hidden rhythm, a kind of secret mathematical language. Well, today, we're going to learn how to speak that language. We're going to decode the simple, beautiful logic that's been hiding in plain sight all along. And it's so true, isn't it? Just think about the elegant spirals you see on a pine cone, or the perfect little hexagons in a honeycomb, or even the way petals are arranged on a sunflower. It's these kinds of beautiful, predictable designs that have fascinated people for centuries. The thing is, they aren't random at all. They follow a stunning logic, and that's exactly what we're here to explore together.
Well, what if I told you that there is a simple language for this, and it's not nearly as complicated as you might think? We're about to connect the dots between that sense of wonder we feel when we look at nature and the simple, powerful logic of mathematics. Let's decode these patterns together. So here's our little roadmap for today. First, we'll uncover nature's hidden code. Then we'll actually give it a name and find the real heart of the pattern. After that, we'll see how these sequences pop up in our daily lives, learn a really powerful formula for prediction, and finally, we'll put all the pieces together into a toolkit that you can use anywhere. Ready?
Okay, let's begin with our first section, nature's hidden code. Think of this as a pattern hunt. And you'll be surprised, I think, to find that these patterns aren't just out in forests and fields. They're right in our homes and workplaces, too.
Just think about these situations for a second. A salary that gets the exact same raise every single year. The rungs of a ladder that get shorter by a consistent fixed amount as you climb up. A kid's money box that grows by the same deposit every single birthday. Even something as simple as the heights of students lining up can sometimes form a pattern. They all share one crucial thing: a predictable step-by-step change.
So, we've seen these patterns are literally everywhere, from your bank account to your garden. Now it's time to give them a proper name. In the world of mathematics, a sequence where the change is this constant and this predictable, well, it's called a progression.
Take a quick look at these lists of numbers. In that first one, it's easy, right? We're just adding 1 each time. In the second one, we're subtracting 30 to get to the next number. What about the third list? We're adding 1 again, just moving up from the negatives. And in that last one, we're adding 50 each time. See? Every single list follows the simple, unchanging rule of adding or subtracting a fixed number.
This special type of list has a formal name. It's called an arithmetic progression, or AP for short. It's really just a sequence where you get from one number to the next by always adding the same fixed number. That's the whole secret, that one consistent step.
And that fixed number, that secret ingredient that creates the entire pattern, is called the common difference. We usually just call it D. And this D value can be positive, which makes the numbers grow. It can be negative, which makes them shrink. Or, and this might surprise you, it can even be 0, which keeps them exactly the same. All right, let's dive into section 3, the heart of the pattern. We're going to take a much closer look at this D value, because really, understanding it is the absolute key to mastering arithmetic progressions. Okay, this is where it all becomes super clear. When D is a positive number, like adding 5 each time, you can see the progression is climbing upwards. When D is negative, like subtracting 30, the progression is falling downwards. And when D is 0, well, the progression just stays right where it is. It's still a perfect AP, just a very, very stable one.
Progressions also come in 2 flavors. A finite AP is one that has a definite end. Think of the rungs on that ladder. There's a first rung and a last rung. The sequence is complete. But an infinite AP, well, it just goes on forever. The classic example is simply counting numbers, 1, 2, 3, and so on, with no end in sight.
And now for the really fun part, applying all of this to the real world. This is where we get to see how this simple idea can be so incredibly powerful for making sense of everyday situations. So, let's meet Reena. She's just started a new job with a salary of 8,000 rupees a month. And her company has promised her a raise, or an increment, of 500 rupees every single year. Her salary is a perfect, real-world arithmetic progression. Let's just track her salary for a moment. In year 1, it's 8,000. In year 2, it's 8,000 plus 1 increment of 500. For year 3, it's her starting salary plus 2 increments. And year 4, it's plus 3 increments. You can see the pattern emerging, right? But writing it out like this year after year, that would be so tedious. There has to be a better way.
And of course there is. We can write this much more efficiently using multiplication. So for her third year, it's the start salary plus 2 times 500. For the fourth year, it's plus 3 times 500. And for the fifth year, it's plus 4 times 500. We are getting so much closer to a shortcut.
So do you see the connection here? It's a little aha moment. For any year you pick, the number of 500 rupee increments she gets is always one less than the year number itself. So for year 5, she gets 4 increments. For year 10, she'd get 9 increments. This single observation, this is the key to everything.
And that brings us right to Section 5, a formula for prediction. By making that one simple observation, we can unlock a powerful formula that lets us predict any term in an AP without having to write out the whole long list. This is where we go from just seeing a pattern to actually using it.
And that simple observation leads us straight to this, the general formula for any arithmetic progression. Now, it might look a little technical, but trust me, we literally just figured this out. The nth term, which is just a fancy way of saying any term you want to find, is equal to a, the very first term, plus n minus 1 times d, our good old common difference.
So let's use it. What will Rena's salary be in her 15th year of work? We just plug in the numbers. We take our starting salary, 8,000, and we add 15 minus 1 times that 500 rupee increment. So that's 8,000 plus 14 times 500, which gives us 15,000 rupees. Just like that. No need to add 500 14 different times. Now that is the power of this formula.
And the formula isn't just for looking into the future, it can also help us understand a sequence that already exists. Like in this garden, the rows of roses form an AP with a common difference of minus 2. We know the first term is 23 and the very last term is 5. We can actually use our formula to work backwards and find n, the total number of rows in the flower bed. It's so versatile.
Which brings us to our final section, putting it all together. You've seen the patterns, you've learned the language, and you've used the formula. So now let's just summarize all of this into a simple toolkit that you can use anytime, anywhere.
So here is your simple go-to test to spot an AP out in the wild. Just pick any number in the list and subtract the one right before it. Then do it again for another pair. If that difference is constant, if you get the same exact number every time, then congratulations, you found yourself an arithmetic progression. It really is that simple.
So you now have the tools to see and understand one of the fundamental patterns of the universe. From salaries and savings to the rungs on a ladder, you can describe the logic and even predict what's coming next. So Michael,